We are going to begin our discussion on the carboxylic acids now. And really, we're going to talk about some of the properties of carboxylic acids. The big property that I think that we should focus on to begin with is that, again, it involves a more electronegative element, that being oxygen. And again, you'll recognize this from the last discussion, this carbonyl group, carbon double bonded to oxygen. The carbon is going to be partially positive because that the electrons are being pulled towards the oxygen, which will be partially negative. This allows us then to have electrophilic attacks occur at that carbon because it's going to be partially positive. So this is basically the center of where chemical reactions are going to occur because of that positive charge right here. So these behave, as you might imagine, based on their name, the carboxylic acids, as weak acids. They are able to release or surrender that hydrogen of the carboxyl group to bases. So this oxygen here can be released, and they're essentially establishing an acid-base equilibrium where this is a weak acid. So you can see that on this slide here with the simple carboxylic acid, acetic acid in water and aqueous solutions. This hydroxide will be lost, and this will form a negatively charged anion. We'll have this positively charged hydrogen, or H3O component. Pyruvic acid, another example here of a carboxylic acid, where it can act as a weak acid. We can also, if we have the basic acid salts, that's essentially when we have that negative charge, but then if there's sodium or potassium in solution, it may associate with that and create a carboxylic acid salt. So when we're naming these, you'll notice ethanoic acid, and instead of sodium, we put that positively charged ion in front, sodium, ethanoate. So we change the ic acid to ate. Carboxylic acids undergo substitution reactions. As I mentioned before, the carbon group over on underneath that oxygen is going to be partially positive, and this is going to be partially negative. And you'll notice that these groups over here that are going to be attaching and replacing that hydroxyl group here, right? These are all also going to be electronegative. So they're going to be partially negative in these conditions where they're attached over here generally. So you'll see that this group, this is what's attaching. These are the other possibilities for those to occur. And essentially, negatively charged groups here are going to be attracted to this positive center of this carbon. It's going to pop off that hydroxide, and usually if these are attached to a hydrogen, that'll form the very stable water molecule. I just want to point out down here, these are going to form some type of amide functional group with a nitrogen. And that concludes what I'm going to talk about right now for carboxylic acids, and we're going to move now into esters, which is a type of carboxylic acid, essentially. Similar to what we were just talking about, those carboxylic acids, as shown on the left here, they can undergo a chemical reaction where then we get the replacement of an OR group that'll come in and attack here. Water molecule will fall off, and then we can create these longer chains of carbon with an oxygen in the middle, and then this carbonyl group here. So these are called esters, where we have two long chains, an oxygen in the middle of those chains, and then a carbonyl group off an adjacent carbon. So these OR groups of an ester do not have the ability to hydrogen bond, remember, because these are, for example, this carboxylic acid, and because it has an oxygen attached to a hydrogen here. once that reaction were to occur, if something were to replace this, and we have an OR group, now there's no hydrogen attached to an oxygen anymore. So we can't have hydrogen bonding. This molecule cannot hydrogen bond. Other things can hydrogen bond with it, but it itself cannot hydrogen bond with itself. Same with this other ethyl ester as well. Same problem. We have these oxygens that are electronegative. They can be polar compounds, but that doesn't mean that they hydrogen bond. Simple esters have a lower boiling point than the carboxylic acids that they are derived from because of that, because of the loss of that ability to hydrogen bond here at the end. You'll notice acetic acid is a boiling point of 118 degrees, methyl ester, ethyl ester, they're in the 57 to 77 range, respectively. Esters are very common chemical reactions that are occurring during the fermentation process and the kind of aging process of many different types of beers. So, for example, in Hefeweizens, a lot of the fruity flavors are coming from esters, and they can also have flavors that are off, but then also really interesting good flavors. For example, so ethanoate is a common ethyl acetate that's found in many different types of beers. So if we're going to look at some of the chemical reactions that these undergo, this is kind of starting with a carboxylic acid and ethanol. So butanoic acid and ethanol, we're going to have this. Remember, this is going to be a partially negative, partially positive group. The negative is going to be attracted to this partial positive. And so those electrons are going to flow towards here. And these electrons are going to flow towards that hydrogen to form this water over here. And then we're left with an ester, ethyl butanoate. Here you notice that is also pineapple oil. So it's going to be a kind of a flavoring of pineapple. Kind of cool. What kind of reaction is this? So take a second. That's an important part of this class is kind of just recognizing, how maybe these things go together, but then what type of reaction is this? So you might have said an addition reaction because we have a butanoic acid and ethanol, and then we end up with the pineapple flavor. But there's also water molecule that forms. So it's actually a substitution reaction because we're actually we're actually substituting these components. So this OH group is going to be substituted for this OCH2CH3 group. So it's actually a substitution reaction and not an addition reaction. Something else I want to describe or explain or point out is that this kind of reaction is very similar to the acetyl formation, where we have this electronegative oxygen is going to be attacking this carbonyl group. The difference is that we actually don't reduce this oxygen bond, right? We actually leave that carbonyl group there. So that's one of the things. It starts with a carboxylic acid, not an aldehyde or a ketone as well. And then it's also a substitution reaction. So some differences here, but also some similarities based on what our starting points are, needing to recognize that there's electronegative region here and an electropositive region here. So here what I want you to do is I want you to first find the carboxylic acid and then look for, also I didn't write this down, the alcohol that is going to react with. So I want you to do that esterification reaction that I just showed you with different compound. So identify the electropositive, electronegative regions, and then what the substitution reaction is going to be. Draw out the final product and realize there's also going to be water it's going to be eliminating a water during that substitution reaction. So take some time, pause it, write this out in your notebook or in your notes, and then unpause, and I will show you the answer to what happens here. All right, so we have this negative going to be positive. We have this as a positive, and this is a negative. This is also going to be negative over here. It's going to be drawing some electrons away. So what's going to happen are these electrons are going to flow towards this oxygen. This oxygen is going to grab this hydrogen. The electrons here are going to move down this oxygen. This oxygen is going to attach up here. So what we're going to be left with is a compound that looks like somewhat like this. Remember, we keep that double bonded oxygen there, and we're essentially replacing it with that OCH3, and we have water. And then when I complete this group, so then that's actually wintergreen flavor. That's what wintergreen looks like. Again, a lot of these compounds are aromatic, and they have these esters that have distinct flavors and generally or smells that are associated with them. So we can also obviously go in the reverse reaction. The hydrolysis reaction is basically where we take an ester and we add water to it. Usually it's involved in, at least in organic chemistry, if we have a somewhat strong acid, we can also we can catalyze this and make it happen a little easier. And we basically replace this, we form an alcohol and also reform the carboxylic acid here. So I want you to look at this problem and what is going to be now the products for the following reaction. And I'm not going to give you the answer. You should be able to do this on your own. If you need help with this, then you can come and see me during my office hours. I want you to look at this also, and this is below. Here's the structure of vegetable oil. What would happen now if we were going to hydrolyze all of these ester bonds shown? I just showed you before that kind of question in the previous slide how a hydrolysis reaction occurs. Pause this, think about this. What is the product going to be, or the products, what are they going to be when all of the ester bonds are hydrolyzed here? Pause, unpause when you've got the answer. What you should have come up with is you have alcohols at each of these regions that were where the ester bond was formed. And this is actually glycerol. This is or glycerine, glycerol. This is that molecule. It's the backbone for fatty acids. And then we also will have these big long chains of carboxylic acids essentially coming off the back end. You should have had large 14 carbon chain carboxylic acids as well. That is what will happen in our bodies when we break down oils. We'll generally hydrolyze these and form these fatty acid carboxylic acids. So if you have a problem kind of remembering this, remember that fatty acid tails, fatty acids, they're named that because they're big long chains of carbon and they have a carboxylic acid tail.